In the warm nights of 1910 in Kumbakonam, India, a 22-year-old named Srinivasa Ramanujan slept on a thin grass mat. He had failed out of university twice, leaving him with no job and no prospects. All he had was a slate and a mind entirely consumed by pure mathematics. One night, Ramanujan had a dream. He saw a snake slithering across a cool stone floor, moving with precision. It eventually wrapped around to bite its own tail, forming a perfectly closed circle. Then the scales began to glow. The snake's body illuminated with 8 distinct lanes of light. As the glow traveled the length of the circle, the body executed a slow half-rotation, twisting back on itself to flip its orientation before completing the circuit. Ramanujan woke up, grabbed his slate, and began to write. He translated the exact geometry of that twisting dream into what he called Mach theta functions. These were incredibly dense equations, but they contained a strange mathematical correction term that he couldn't fully explain. For 80 years, that specific term sat in his notebooks as a purely mathematical curiosity. He had recorded the signature of a highly specific geometry. However, he left the world with a puzzle. He had the math for a shape, but no one could find its physical counterpart in the real world. Decades later, halfway across the world, physicists like Richard Feynman were dealing with a completely different problem, trying to write the rules for subatomic particles. At the quantum level, particles like electrons don't act like solid objects. They behave like clouds of probability. To make the math work, physicists had to accept bizarre rules, like the fact that an electron has to spin 720 degrees, 2 full rotations, just to return to its original state. Science eventually settled on the idea that the subatomic world lacks a physical, tangible geometry. We treated these rules as abstract mathematical probabilities, rather than descriptions of a real, three-dimensional structure. Curious, leaning in. But that 720-degree requirement is a specific geometric constraint. It raises the possibility that we haven't been looking at abstract math, but rather the blueprint for a physical shape we've been missing. To find that shape, we have to start with a single, radical premise. Imagine that space is not a container, but an emergence. Imagine that time itself is a one-dimensional, tensioned string. This diagram illustrates the core physical rule of that time string. It is pulled taut, and its tension is exactly equal to the speed of light. When mass energy interacts with this time string, the string is pushed and deflects into a parabolic curve. This curve immediately opens up new dimensions. The interior of the parabola defines a radial direction and an azimuthal direction, while the string itself provides the third, the axial length. The 3 spatial dimensions we experience are the direct geometric result of this 1D string bending. Space is the shape of the deflection itself. This 3D model shows what happens when that deflected string closes on itself to form a stable particle. To maintain the right orientation, the loop has to twist, forming a non-orientable surface like a Mobius strip. This physical twist explains the 720-degree spin. A path on this surface must revolve twice to return to its starting point. Waves traveling inside this parabolic twisting shape experience specific geometric interference. This interference forces the waves into the exact mathematical patterns we see in quantum angular momentum. When you map the optimal pathways across this surface, you find a structure with 8 distinct lanes tracing a twisting loop. This is the co-prime architecture, the same 8-lane pattern Ramanujan saw on the glowing snake in his dream. The baffling mathematical correction term in Ramanujan's equations represents the physical twist in the Mobius strip. It is the geometric requirement for a stable quantum particle. If this twisting geometry is the fundamental architecture of the universe, it should be observable at all scales. We should be able to find evidence of it in the macroscopic world. This circuit diagram outlines an experiment built to test that theory. It uses a bipolar Hall effect sensor, a chip designed to measure magnetic fields, powered to its full 12-volt limit to map the space around an ordinary magnet. The methodology is rigorous. By keeping the sensor at a constant fixed angle and moving it through space, researchers can detect precise three-dimensional variations in magnetic polarity. At each measurement point, the sensor acts like a local observer. Every time the LED lights up, the field's information collapses into a specific, measurable physical location, mirroring the behavior of quantum observation. We typically visualize the magnetic field around a bar magnet as a uniform, invisible bubble. However, the data from the Hall sensor mapping reveals a far more complex structure. This side-by-side comparison shows the theoretical s, p, d, and f atomic orbitals of hydrogen next to the 3D maps generated by the magnet. The macroscopic magnetic fields precisely mirror the multi-lobed geometries of the quantum world. These 3D maps are direct physical detections of the field structure. They indicate that the same geometric constraints and harmonic solutions that define the atom also define the field of an everyday magnet. From Ramanujan's 1910 dream, to the deflecting string of time, to magnets on a refrigerator, the evidence points to a single conclusion. The universe is governed by a shared physical geometry that we can finally see.